Welcome, Chem 1. In Unit 11, we took a look at gases and their properties. Today, we start Unit 12, which is a closer look at solids and liquids. Let's get started. In order to take a closer look at solids and liquids, we're going to start by focusing on how molecules of solids and liquids interact with each other. Why do solid molecules hold on tightly to each other and form rigid structures, and why do liquids hold on less tightly and allow molecules to move past one another? To do this, we're going to revisit and review intermolecular forces. Hopefully you remember that the type of intermolecular force goes all the way back to bond polarity, about how two atoms interact and the type of bond they make. We can determine the polarity of the bond by looking at the electronegativities of the atoms in the bond and subtracting those electronegativities and looking at the type of bond they create based on their electronegativity difference. So hopefully you remember that electronegativity is the ability to attract electrons. So when there's a great difference in electronegativity, one electron is going to win the tug of war and pull electrons toward it with greater strength, and another atom will have less electrons around its nucleus. So if both atoms involved have very similar electronegativities, or a difference in electronegativity that's less than 0.4, then they're going to share electrons evenly. There's going to be no charge present. We call this a nonpolar covalent bond. They're sharing equally. If there is a slight electronegativity difference between 0.4 and 1.7, that means those atoms are still going to share, but one atom is going to win the tug of war. We call this a polar covalent bond. In this situation, there's going to be a positive end of the bond and a negative end of the bond. And then finally, if the electronegativity difference is greater than 1.7, that means somebody is completely winning the tug of war. We're going to have someone gain, someone lose, and this is an ionic bond. Positive and negative charges are still present, and ionic bonds still have polarity because of those positive and negative charges. After we've identified the polarity of the bonds, we then have to look at the entire molecule and see if the molecule is polar. First, if you have nonpolar bonds, then it is a nonpolar molecule. You cannot get a positive and negative end if all the bonds within the molecule don't have positive and negative ends. Nonpolar bonds equals nonpolar molecules. If we have polar bonds within the molecules, then we'll have to look at the shape of the molecule to determine if we have a polar molecule. We determine the molecular polarity a couple different ways. The first way is to draw the Lewis structure of the molecule and see if the molecule passes the straight line test. If you can draw a straight line through the molecule separating the positive from the negative end, then that's going to be a polar molecule. Another way to do this is to look for a lone pair. If you have a lone pair around the central atom and polar bonds, this is also a good indication that you have a polar molecule. All right, so we've determined the bond polarity. We've determined if the molecule we're looking at is polar. Now we need to figure out what this means for our intermolecular or attractive forces. Remember, intramolecular forces are forces within the molecule. These are bonds, ionic, covalent, metallic. But intermolecular forces are forces in between two different molecules. We have dipole-dipole, London dispersion, and hydrogen bonding. Intramolecular forces, or bonds, are stronger than intermolecular forces. The weakest intermolecular forces are London dispersion forces. These occur between nonpolar molecules, and they're caused by electrons moving around and causing instantaneous dipoles. These are positive and negative pockets within a molecule that come and go very quickly. Because this isn't a consistent dipole, London dispersion forces are very weak. The more electrons present typically increases the strength of these LDFs. The next type happen with polar molecules. We call these dipole-dipole forces. A polar molecule has a positive and negative end and will interact with another polar molecule that has a positive and negative end. Because the dipoles are consistent and continuous, these dipole-dipole forces are much stronger than a London dispersion force. The higher the difference in electronegativity, the stronger these dipole-dipole intermolecular forces will be. And finally, we get the strongest type of intermolecular force, hydrogen bonding. Hydrogen bonding is simply just a dipole-dipole force that has a very large electronegativity difference. This happens when hydrogen bonds to oxygen, fluorine, or nitrogen. Whenever you have hydrogen bonded to one of those three in a molecule, you get great electronegativity difference and lots of polarity within the molecule, which creates very strong intermolecular forces, which we call hydrogen bonding. So let's take a look at some of these compounds. The first one here is BF3. If you subtract the electronegativity of boron and fluorine, you get a difference of 2.0. That's a very large difference. This bond would be considered ionic. If we draw this out, you should remember that boron is stable with 6 valence electrons around it, meaning that this is trigonal planar. There is no lone pair around the central atom, and therefore, even with polar bonds, this is going to be a nonpolar molecule. And therefore, LDFs would be the only intermolecular forces present. Now let's take a look at water. If we draw water correctly, you would see that it has 2 lone pair on the top of this oxygen. This is what pushes it into a bent configuration. You could also subtract hydrogen from oxygen and see that the difference here is a 1.4 difference. This would be a polar covalent bond because it's between 0.4 and 1.7. So, since we have lone pairs around the central atom, since we have a polar covalent bond, this would be a polar molecule. This polar molecule would have LDFs because LDFs always exist in every molecule. It would also be dipole-dipole because of the polar molecule. And it would have hydrogen bonding because hydrogen is bonded to oxygen in this case. I know that most of today was review, but understanding these intermolecular forces in solids and liquids is really going to help us understand their properties. Complete the activity for this section. Let me know if you have any questions. We'll see you soon.